Okay, last time we talked about sequential compactness, and this is a new concept that we're going to use to substitute the compactness. And we also said that a sequential compactness is equivalent to totally boundedness. And here we're going to discover more of their properties, and then we can see why this sequential compactness can be a very good substitution of the compactness for this course. Okay, first we recall the definition for separable sets or separable space. Suppose we have a metric space, then X is called separable if X contains a countable dense set. Okay, so you have seen this definition in analysis and also real analysis, so I will not repeat or give you more examples. And an important property of totally boundedness is that every totally bounded space is separable. So this is going to be given by the following theorem. Okay, the proof is actually very simple. Okay, imagine that we just need to find out, a countable dense set for this X. Okay, and to do that, we first notice that since X is totally bounded, that means for any K, there exists a finite 1 over K net. Now we call this net nk. That means this X is covered by this 1 over K net, so that if you search for any, you go over all the elements in this nk, and you draw a ball centered at each of these points in nk with the radius 1 over K, then you can know that the union of them will be able to cover this X. Okay, and this is finite, meaning that each of these has only finite many points. Okay, so basically that means if this is the X, then you decide the K to be specify any K, then you will be able to cover this X using finite many of these balls with the radius 1 over K. Okay, so that's what we know. And now you can see if I take the union of these nks, so this union of this nk is from 1 to infinity. And this will be able to cover, this will be a dense subset of X. The reason is that you look at any point Y in this space X, then you know that for any epsilon ball you draw around it, you know there exists some K large enough such that 1 over K is smaller than epsilon. But this Y can be covered by this Y is this Y is one of the points in here. That means it can be covered by a finite many balls like this. Okay, so that means at least the Y is inside one of these balls. But these balls all have a radius even smaller than epsilon. That means there will be some Y, say I call it the YK, for example, and the radius, the Y is inside the ball centered at YK with the radius 1 over K. So it's like that. And this radius is just 1 over K. since it's even smaller than epsilon, so you know that the yk must be inside the ball by epsilon. Okay, so that means for any y and for any epsilon, we can find some yk, which is from the union of this point, union of this epsilon nets, so that union of this 1 over k nets, so that this y contains a point from there, from some point in here. Okay, so this is a dense set of x, and obviously it's also finite. It's also countable because each of this is finite. And you take a countable union of finite sets, this is still countable. So this whole thing is countable, and that's why we show that this is just a this x is a separable. Okay? The space x is separable. Okay. Again, recall a definition of a compact set, and this is also something you're very familiar with. So let X D be a metric space. Everything's a standard. Then M as a subset of X is called compact if any open cover of M has a finite subcover. Right, this is what we define for compact sets. This is a very important concept in analysis, but what we're going to show next is that if we have a metric space, then compactness is equivalent to sequential compactness. And that is very important. So that's why we can substitute the compactness by sequential compactness in our later study. Okay. Suppose we have a metric space, be a metric space. This M is a subset of X, so this M is compact if and only if M is sequentially compact. Okay, so now let's see how to prove this. Let's first prove this direction. Suppose we know the M is compact. Let's show that it's also sequentially compact. Okay, let's do this proof by contradiction. Suppose not. So M is compact, but not sequentially compact. So what will happen is we'll look at M. There is a sequence we call xk. That is that's a sequence in M. The every put just means every term is from M, and this sequence does not have any convergent subsequence. Right? When we say the M is compact, means that every sequence has a convergent subsequence. If it's not sequentially compact, that means there exists a sequence in M that does not have any convergent subsequence. Okay? So it's M. Say, then there exists some sequence in M such that which does not have convergent subsequence. Okay, since it doesn't have any convergent subsequence, it doesn't have any accumulation points. And this means that this, if we collect all these points as a set, it doesn't have any accumulation point. And this means that S itself is closed. Okay. So let's define S to be this, then S is closed. Okay. Because the closed set means that any accumulation point is included in the set. but it doesn't have any accumulation point right now, so it says S here is automatically closed. Or if it's closed, and then we can define the SK, which is just the same as, but take out this XK. Okay, just take out 1 point from S. And apparently this is SK is still closed. Okay, the SK is still closed. Well, because it's closed, the complement of SK will be open. So the X minus SK, which is just a complement of SK, is open. Okay, and now let's consider the union of this this thing. Okay, so let's say take the union of this, which is X minus SK. So actually, you can see what this union is. Let's say I can rewrite this as the union of X, the intersection of SK complement, right? And then I can use the distribution law of this intersection union. This becomes the intersection of X and the union of SK complement. Okay, it's from 1 to infinity. And then I know this is just the X intersection with the intersection of K from 1 to infinity SK complement. And then this, by definition, is just the X minus the intersection of K from 1 to infinity SK complement. No complement now. Right? So that's the. Okay. Then recall that SK is just the sequence right here. But so this is the S right here. And you take this XK out. So every time you take it 1 out, and then you take the intersection, you can see that S1 is just say X2, X3, so on and so forth, and S2 is X1, X3, so on and so forth. So if you take the intersection of those things, you will see that no one is in every one of them. There must be one missing, so that's why this whole thing is just an empty set. And then that implies that this is just X. And since M is a subset of X, so this means that, right? Okay, and what this means is that this is open, and we found an open cover for M. And because M is compact, we know that we can find a finite subcover from here. That means we don't really need infinite many of this to cover the M. We only need finite many of them. So let's say that I only need let's be conservative, which is limit the first K of them. There exists K such that the M is included or is covered by the first K of these sets. Okay, and now let's find some contradiction. On the one side, we know that when we look at this right hand side here, again, following the same structure, we can easily show that this is just the X take the intersection of the union of SK complement. K is from 1 to capital K, and then we can show that this X minus the intersection of SK from 1 to capital K. Okay, now look at the intersection of this. Remember again that each SK is just the original sequence S without the XK term, the kth term. So if we take the intersection of this whole thing will be just XK plus 1, starting from XK, capital K plus 1. So this thing here is just X capital K plus 1, X capital K plus 2, and all the later ones. And then we're taking them out of this X. So then that means X capital K plus 1 is not in here anymore. So X capital K plus 1 is not in this set. It's not in this one here. Okay, but on the other hand, we know that we chose this sequence from the M. So that means XK as one term in the sequence must be in here. So it's in the left side, but it's not in the right hand side. That's a contradiction. Since the left hand one, this one is included in this one. Okay, so that's where the contradiction is. So, And this means that the set M must be also sequentially compact. So M is sequentially compact. Okay. So now let's show the other direction. Now we assume that this M is sequentially compact. Let's show that it's also compact. Okay, first of all, we showed before that this M is sequentially compact, then it must be totally bounded. Okay. Suppose M is sequentially compact, then M is totally bounded. Okay. That means every epsilon we can find a finite epsilon net for it. Okay. Now again, we prove the compactness by contradiction. Suppose that M is not compact. And that means there exists a open cover, but it doesn't have any finite subcover for M. Okay, so let's say this open cover is G alpha, and this A is the index set. It's an open cover of M, but it does not have any finite subcover. Of M. Okay, so now let's again try to find some contradiction. So on the one hand, we know that M is totally bounded. That means for any K, totally bounded, we know that for any K, there exists a finite 1/k net. Let's say this net is nk of M. Again, this is because this implies that the M can be covered by finite many balls, where the centers are from this net, and the radius 1/k. Okay. Implies this. Okay, so what do we mean? But here is that, say we have this M, this is a set M, and it can be covered by finite many of these balls with the radius 1/k. Okay, for each K we can do this. Let's just fake any specific K, we can do this. Well, if all these balls, can be covered by finite many open sets in here, then that means we can find a finite open cover for the M, because this epsilon net, these balls, they can cover the M, and there are only finite many of them. We can use them to cover M. But if on the other hand, if each of these balls can be covered by finite many of this, then take the union of those, it will be a finite open cover for M. But we said that this one doesn't have any open cover. That means at least one of these balls, that means one of these things, they cannot be covered by finite many balls, or finite many sets in here. Okay, so that means there exists M is not compact, as we assumed. There exists at least one of these balls, like let's call the center is yk from nk, such that the byk over k cannot be covered by finite many open sets in this collection, in this open cover. Okay, now for each K we can do this. Okay, so we can form a sequence, because for K equals to 1 we can get y1, k equals 2, we get y 2, so on and so forth. So we get a sequence. Okay. Consider the sequence. Okay. Now notice that with in this case we know that the M is sequentially compact, and now we have a sequence. That means this sequence must have a convergent subsequence. Has a convergent subsequence. We call it the YKJ, and also a point Y from the set X, set M, such that my YKJ will converge to Y. Okay, so now let's look at this Y. Because Y is in M, and M can be covered by this open cover right here, so that means the Y is in at least one of these open sets. Okay. So Y is in M, and that's in the union of G alpha, where alpha is from A. That means there exists at least one alpha. Let's just say this is one alpha, such that, or alpha prime, such that there exists some delta in the also this B I'll say there exists some delta satisfying the BY delta is inside the G alpha. So G alpha prime. Okay, and the reason is, again, as I said, since the Y is inside the G alpha prime, so right here, and the G alpha prime is open, so that means I can draw a ball here with the radius delta, so that the entire ball is inside the G alpha prime. Okay, and now we look at this ball. We know that the sequence Y, the sequence YKJ, is converging to Y. So that means I have a sequence that is converging, is getting closer and closer to Y. So that means up to some point, the sequence will fall into this ball. And more specifically, I know that there will be a point in here with the radius small enough such that the entire ball centered at one of these points with a very small radius is also in this Y. Okay, so there exists J large enough such that the BY Kj and the 1 over Kj is so small that it's included in the BY delta, and that it means it's inside the G alpha prime. Okay, and that is a contradiction to our assumption earlier, because we said we chose this YK, this sequence, a term in the sequence, such that this ball cannot be covered by finite many open sets in here. But now we found one that is covered by just even one of them, one open set from the open cover. And that is where the contradiction comes from. So this is a contradiction to the choice of our sequence YK. And because of this, we know that the M must be compact. It's our assumption right here does not hold. Okay. So M is compact. Okay, so this completes the proof. So now we can see that sequential in metric space, at least this is where we're studying in this course. As long as we find a metric, then the sequential compactness is equivalent to compactness. So we can use them interchangeably. All right. So now let's consider a generalization of. So we all know that this means the set of continuous functions defined on the interval AB, right? So this is what we used. So this is the mapping from the interval AB to a real number such that the F is continuous. Okay, so can we extend this to a more general setting? Say we're not interested in this A interval AB, but we're interested in more general metric space. Then let's say that we have a metric space that is compact. Let M be a compact metric space. So I should specify that X and also the D. This is my distance on this metric space. And then let's consider the set of continuous functions defined on M. Then the Cm is the set of continuous functions defined on M. So M is right now is a general metric space, but it's compact. The F is continuous. Okay, so this M is to substitute or to generalize this one here, and this is apparently it's a compact metric space. We use the standard metric. Now we have a general metric space, but it's also compact with the distance or metric D defined over there. Then we can define the Cm. And in the over the Cm, we can define a metric just like what we used or the metric we used to define for this. Right? We said the metric over this C is that we used the D there before. Let's just don't be confused with this D here. So this D is a metric we used for this space. We said X and Y is defined to be the maximum of the distance between xt and yt, where t is between a and b, right? And now we're going to define a similar metric here. Suppose we have two functions from the Cm, say u and v, and we're going to define the metric over this Cm by the maximum of this u, say I say u, should I use t or some, I don't want to use x now, let's say use c, minus v c, where c is from M. Okay, and then we can easily show that this Cm with 0 is a metric space. Metric space. And actually you can easily show that this is the metric. You can show that this is greater than or equal to 0, positive definite, symmetric, and also satisfies the triangle inequality. The only issue is that right now, can we really get this maximum like we did here? Okay, and you can see because M is compact, so if you're familiar with topology, you can directly say that since this U is continuous, V is continuous, the difference of them is continuous, and then you take the absolute value is still continuous, so essentially here is a continuous function of C. And then this M is compact, so you definitely can get maximum, reach maximum at some point, yeah, right? But also we can use what we just proved. We show that the compact means the sequential compact, okay, are equivalent to our compactness. That means if I want to show that the maximum here can be reached, we just need to show that, well, if we can really find some point C such that if I used to define this as the infimum or supremum, sorry, C in M, U C, V C, can we really replace this supremum by C, by maximum? That means can we really find the C, some point C over the set M such that this is equal to equal to the maximum. And to show this, we can easily see that since if we define this as a supremum, that means I can find a sequence. I would say the UK, VK. They're all from the Cm. Sorry, I should say. What I'm doing here. So for any fixed U and V, I want to show that the supremum is actually maximum. And to see that, we just need to see that there exists a sequence, I call it CK, which is from the M, such that the U CK minus V CK, this is converging as k goes to infinity, this is converging to the supremum U C minus V C. Right? This is the definition for supremum. You will be able to getting closer and closer to this, arbitrarily close to that, and using a sequence. Okay, and since we know that these CK are from M, which is compact, so that means but M is also sequentially compact. That means I can extract a subsequence, which is convergent. So I can exist a subsequence. I call it CKJ, and such that the CKJ is converging to some C. Let's say C star. And this is also in M, since M is sequentially compact. And then from here, we can see that since if we plug in C, K, they will converge to that. So if I plug in a subsequence CKJ, it's also converging to that, right? So in that case, we just have the U CKJ minus V CKJ. And as j goes to infinity, it's also converging to that. U C minus V C. Okay? But on the other hand, we know that since CKJ convert to C star, this also convert to C star. They both converging to C star, and the U and V are continuous. So that means this thing converges to U C star, and this convert to V C star. And the difference of them, take the absolute value, they convert to that. So on the one hand, they convert to this, and on the other hand, they convert to that. Okay, so that means these two are equal. And this C star is some point in M. That means we can actually just evaluate our U and V at that point C star, and this value, the difference of the absolute value of their difference will be exactly this one. Okay, that's why this. So this convert to U C star. This convert to V C star. So the difference between these two is just the supremum. U C minus V C. C is from M, and that means this supremum is actually maximum. All right, so that's how we show that this is a metric space. So the only thing, as we said, the only thing to show this supremum is essentially just maximum, and then triangularly, it is easy to show that the rho is a metric, and then this is a metric space. Okay, but not only that, we actually can recall that if you use this as the metric, this is a complete metric space, and similarly here we can show that this is also a complete metric space. Okay, and I will not go through the proof, but this almost identical to the proof for this one, for this metric space to be complete, as we showed in I think in the first lecture. A second lecture. Okay. So remember, it's a complete metric space. Now we're going to give a last important result in this subsection, and it's called the Arzela-Ascoli theorem. It's a very important theorem analysis. Before that, we're going to give two definitions first. So now we assume that we have this Cm. The M is compact metric space, so MD is compact metric space. And then the rho is defined as we did earlier, so this is the complete. Itself is a complete metric space. Okay. And in this metric space, we can consider subsets. Okay. Now in this case, it will be a subset of functions, since this is a set of continuous functions. Okay, it's a subset of that, means a subset of continuous functions. And we call let f to be a subset of Cm, so it's just a collection of functions right now, collections of continuous functions defined on M. And then we say this f uniformly bounded. F is called uniformly bounded if there exists some use the bound L such that no matter which function you're picking from this capital F, and no matter which point x is from the M, this is always bounded by L. Okay, this is true for any x from M and any f from this collection. In this case, we'll call the function uniformly bounded. We can also still the same setting. F is a collection of functions, continuous functions. And then F is called equi-continuous. So equi-continuous means that they are basically means that they're equally continuous. Okay? They're basically at the same continuous level. And to be specific, what this means is that for any epsilon greater than 0, there exists some delta which depends on the epsilon. So I write this such that no matter which function you pick and no matter which 2 points you pick from the M, you always have the fx and fx prime. These 2 points you pick up from the set. This is always less than epsilon. Okay? For any x prime from the M, where the distance is less than delta, and for any f from that. Okay? So that means there exists a universal delta here, such that as long as your 2 points are not far away, their distance is less than delta, and in this case, no matter which f you pick, you look at, their disagreement is smaller than epsilon. So this is why we call it equi-continuous or equally continuous. All right, so why we're introducing these two? This is the essential part for the Arzela Ascoli theorem, as we show right now. Okay, this is a very famous theorem analysis. So what it says is that if we have a family of a continuous function, just the same as before, over M, then F is sequentially compact if and only if F is totally bounded, uniformly bounded and equi-continuous. Uniformly bounded, and also F is equi-continuous. Okay, now let's prove this. Remember that we said the sequentially compact is means that it's totally bounded, right? It means that it's totally bounded. So we can actually replace this one by totally boundedness, and then let's just replace this one by totally bounded. And we were using this totally bounded instead. Okay. Now we first show this direction. Let's assume that F is totally bounded. Then we want to show that it's uniformly bounded and also equi-continuous. Since it's totally bounded, then uniformly bounded is really straightforward, right? It's obvious. It's uniformly bounded. And we just need to show that it's also equi-continuous. And to show that, let's say that for any epsilon, we're going to do this, right? We're going to find a delta such that this is less than epsilon no matter for all the x prime with distance less than delta and NF. Okay, that's our goal. Okay, so because the f is totally bounded, we know that for this epsilon we can find a finite epsilon net, or right now I want a third of epsilon net. Okay, there exists a finite net, epsilon over 3 net. We call it the phi 1, phi 2, and the phi k. Okay, what this means is again this f can be covered by the balls centered at those points with the radius epsilon over 3, k from 1 to capital K. Okay, this is what we mean by that. Okay, now let's look at these functions. For each one of them, because they are continuous functions defined over a compact set, we know that they are uniformly compact. Uniformly compact means that for each one of them, say for example the kth one of them, there exists a delta k such that the phi k x minus phi k x prime will be less than epsilon. I want it to be epsilon over 3 right now. For any x prime from M, and also the distance between x and x prime is less than delta k. Okay, I can do this for any k. For any k from 1 to capital K, I can do that. And now I just need to choose my delta to be the minimum one of them. So then this delta will work for everyone. Minimum of delta 1 to delta capital K. Since we have finite many positive numbers, so the minimum of them is still positive, then I know that the phi k, that means just the line above will hold for any k. Okay, this will hold for any k. So let me still write it, but you know what the already know right here. And also this k, okay, we know this. Okay, so now we can estimate the this delta will be what we need. For this delta, as long as x and x prime has the distance less than delta, we can show that f x minus f of x prime, no matter which f is from the M, we can show that this distance is less than, we know because the M has a finite, sorry, this is not M, it's the capital F. Because this F is covered by this, so that means for any F in this family, it must be inside one of these balls. So there must be some k such that the little f is in one of these. Okay, so let's say that this f is in the phi k. Okay, and we're going to have this f of x minus phi k of x. I know that the distance between this f and the phi k is less than epsilon over 3. Because this f is in here. My f is in one of these balls. Let's just say this, and then we have the phi kx minus phi kx prime, and then the phi kx prime minus f x prime. So you see this trick a lot before, right? Since we are trying to estimate the distance between the two, so we use some help from the delta k of the phi k. We know that the f is really close to phi k, means that for every point over the M, the distance between f of x and the phi k of x is smaller than epsilon over 3. So that means this one is smaller than epsilon over 3, and this one is also smaller than epsilon over 3. And this one here, we know that it is also smaller than epsilon over 3, as we showed here, because this delta was chosen so that no matter which k we're talking about, this is less than epsilon over 3. Okay? So all of them are less than epsilon 3, so together it's less than epsilon. Okay, so this means that no matter which f we're talking about and no matter which delta x and x prime, as long as their distance is less than delta, then we can have these 3 terms bounded by epsilon over 3, and then totally is bounded by epsilon. And that shows this direction from left to right. Okay, now let's show the other direction. Okay, to show this direction, let's say that what we need to do is for each epsilon, we want to find a epsilon net. Okay, for each epsilon, we need to find a epsilon net for this f. So we're going to use a similar trick. Right now that to find a epsilon net, we need to find a finite epsilon net. To find that, we need to show that for every f, we can find some, say, phi 1 through phi, say I used m. I want to figure out, for every epsilon, I want to figure out some, or want to find some functions phi 1 through phi m, such that any f in M must be inside one of the balls centered at this phi's with the radius epsilon. Right? We need to find phi 1, phi m, such that as long as I have finite many of them, so m, as long as it's a finite number, I want to show that this f is shown to be covered by this epsilon net, the b j epsilon. Okay, that's what we hope for. And the question is, how do we get that? Okay, and this is a little bit tricky because not only we're trying to get this to x, but we also want to show that this phi is close to f universally over or uniformly on this M. It's the distance is epsilon. That means no matter which point over M we're looking at, which point x we're looking at, the phi j of x minus f of x will be less than epsilon. Okay, the x can be any point on M. Okay, so that's how we're going to show how we do this. Because the f is equi-continuous, this is what we know, as it's equi-continuous and uniformly bounded. So the f is equi-continuous. We know that for any epsilon, as we said earlier at the beginning, there exists a delta, which is delta epsilon, such that the f of x minus f of x prime is less than epsilon over 3 for any x prime in M, and also the distance between x and x prime is less than delta. Okay. So this is what we know about using the equi-continuity of this family F. Okay. And on the other hand, because it's M, D is compact. We just show that it's compact set, it means it's sequentially compact. And it's also totally bounded. Okay. It's also totally bounded. Okay. And that means for this delta right here, we can find a delta net. So there exists a delta net which we call x1 through xn. That means the M can be covered by the balls centered at xi with the radius delta, I from 1 to n. Okay, so this is my delta net. Okay, and that means for any point in M, it must be inside one of these balls. Okay, now let's look at the mid mapping. The T has a mapping from Cm to Rn. So the n is the number of points is in this delta net. Okay, how we're going to define this T is that, say, any continuous function in Cm is mapped to a vector, n-dimensional vector, by evaluating this phi on these points on this delta net. Okay, this is the n-dimensional vector. Okay, this is how we map any function in this, or any point in this space of functions, to a real vector by this. So apparently this mapping is surjective, or is onto, meaning that for any value right here, I can find phi such that this T of phi, which is here, is taking that value. So the reason why this is obvious is that, say this is the M, and I have these points, these many points, I have 8 points over this, for example. Then we can find any continuous function. The phi can be any continuous function defined on M. So we're going to take some values here, and I'm just extracting the values, or evaluating the phi at those points, and then we're going to form a vector right here, 8-dimensional vector. So apparently that I can always just vary my function phi so that I can take any vector here. For any vector here, I can try to find a continuous function phi over this, defined over this M, so that when I evaluate that phi over these points, you get the exact value there. Okay, so this is surjective mapping. So the T is a surjective. Then T is surjective. Okay, for any vector in Rn, I can find some continuous function defined on M, such that this is equal to that point. Okay, so why I'm doing this? By doing this, I can actually consider the sequential compactness not in or totally boundedness not in this this Cm, but instead I can consider that in Rn. Okay, but Rn is much easier to handle, and to that end, I need to use the uniform boundedness for F. Okay, since F is uniformly bounded, so that means there exists some L such that the F, that's called the definition, this is less than or equal to L for any X in M and any F from a family. Okay, and now you can see what happens when I map this F to by T. So because now I have F from here, and then it will be mapped to some vector. So let's look at the TF. So according to the definition, TF will be just the F of x1, right, all the way to F of xn. This is the vector. Okay, but I know that each one of them has a magnitude L. So this one is bounded by L, this one is bounded by L. So I have in total n of them. So when I take the F's value, or take the norm of this n-dimensional vector, I know each one of them is less than M. So this whole thing will be less than equal to square root of L squared all the way to L squared. Okay, and this is equal to square root of NL. But anyway, this is the finite number. This is the finite. So no matter which F I'm looking at from the family, they are going to be mapped at some point, within the cube of the Rn. Okay, so that's what this one is. And now let's look at the range of this T, or the image of T, image of F under T. So now the T of F, this is like the image of F. I know that every one of them is bounded by here, so this one is completely inside a cube. This is inside a cube in Rn. Okay, and because it's bounded, I can take the closure of this, and this will become a closed bounded set. And we know that this closed bounded set in Rn is compact. This is closed and compact and bounded in Rn. So that means the TF is compact. And it's compact means it's also sequentially compact, because we're in Rn, it's definitely a metric space. And it's compact means that it's sequentially compact. And it is also totally bounded. Okay, so that means it's totally bounded. Well, with this, because it's totally bounded, I know that for any epsilon, I can find a finite epsilon net. Okay, so there exists a finite, now I have not epsilon net, but epsilon over 3 net. Let's say that the epsilon net is formed by phi 1, phi 2 over phi m. This is going to be my epsilon net for F in the origin space. Let's see why that's true. But the S will be a finite epsilon net for, let's see how I call this function. Epsilon net phi let's call it phi 1 through, or maybe use y1. y1 through ym of this TF complete closure. Okay, remember that everything right now is in Rn. So this is every one of them is in Rn. Okay, and this form a epsilon over 3 net for the TF. So that means the TF, right, continuously here, see it's in the union of this J epsilon over 3, J is from 1 to m. Okay, the points right now is that these points are in Rn. And I know we showed that T is a surjective mapping. So that means each one of this Y, they're corresponding to some phi in Cm. Let's say this is the phi 1 all the way to phi m. So it means that this is just equal to T phi 1. This final one is just equal to T phi m. Okay? And now I have this phi 1 through phi m. I'm going to show that this will be my epsilon net for the family F. So let's show that this is an epsilon net of this family F. Okay, I want to show this is epsilon net for a family F. Well, to show that, we just need to show that the F is included in this phi j epsilon for j from 1 to m. Sorry, write the j is from 1 to m. Okay, I need to show this. Well, to show this, I just need to look at this F. I know that my F was mapped to the TF. Okay, my F is mapped into TF, so my T of little f will be inside inside here. So that means it is inside this. Okay, inside union of this. That means it's inside one of these balls. It's the one of these balls. Okay, let's say that it's inside. Let's say that TF is inside the ball center width YJ. Let's say that. Then this YJ is corresponding to a phi j. So now let's look at the distance between F and phi j. Okay, and this X can be any point because I want the uniformly close to the phi j. So let's just look at this. Okay, so on the one hand, because X is a point in M, and we had a epsilon, we had a delta net before, right? I think where we have that. So this is my delta net. Okay, that means my M is covered by this. So that means X, if X is a point in M, it must be inside one of this. So let's just say that my X, for any X, I know that it's inside one of this. So let's just say that's the xi delta for this X. Okay. So here I'm going to do, again, the same trick, f of x minus f of xi, then plus f of xi minus phi j of xi plus phi jxi minus phi jx. Okay, now let's see. Because the delta was chosen from the equi-continuity. So this means that x and xi has a distance less than delta, but this delta was chosen such that this is less than. As long as the 2 points are not far away, like these 2 points, like this x and xi, then the distance between them will be less than epsilon over 3. So that means this first term is less than epsilon over 3. And let's look at the last term. Again, because the xi and x, their distance is less than delta. We can also show that this is less than epsilon over 3. Okay. And the only thing left is to show this one. This is the most troublesome one. How do we show this? And this is we're going to bring back what our t had before. Remember that the t of f minus t of phi j, their distance, because each one of them is mapped to a vector f1 to f xm, so xn, minus phi j of x1 so phi j of xn, sorry. So there's difference to vectors. We know how to compute their distance, right? But at least their distance is bigger than the f of xi minus phi j of xi. So that means this middle term right here is smaller than this. Okay? But we said that, or TF was chosen from here and that it is inside one of these balls. So that means the TF and the YJ has a distance less than 3 over epsilon over 3. But this YJ is just this. This is actually the YJ. Okay, so that means this distance is less than epsilon over 3. Sorry, epsilon over 3. Okay, that shows this is also less than epsilon over 3. Okay, now we have 3 of this, then the whole thing is less than epsilon. Okay, and that completes the proof. Because right now we show that for any epsilon, we show the epsilon net, which is this. Okay. So the key is to find out this tree. I think this is very clear. This is clear now. This, I would say, you can see that the xi, the delta was chosen before only for the family f, so that this first term is less than epsilon. But since we have a finite many of them, of these functions, and all of them are continuous as well, so all of them are uniformly continuous, and each of them have their own delta k, as we did before. This one has delta 1, this one has delta m. So we can choose the delta. We can further shrink the delta to be the smallest one among the delta, and this delta 1 to delta m. So in case you say I have a delta 1 to delta m, I take the smallest one, I call it the delta prime. And then I also take the smaller one of the delta I had earlier and this delta prime to form the new delta. In this case, this will be also less than epsilon over 3. This is also less than over 3. Okay? And this term, again, is what I showed before, right here. Okay, that completes the proof. Okay. Now let's look at some applications of that. So first, let's look at an example. Suppose I have omega, which is open and convex. Okay, and also I have L0, L1, which is bigger than 0. So now let's consider the set. Define a set F to be a subset of C1 omega, where the function values are bounded by L0, and the derivative, or the gradient, I should say, the gradient of F, they're bounded by L1 for any x. For any x in omega. Well, you probably wonder why we were specifying this to be open. We don't have to, but it's just that when we specify this open, then we're clear that we take the closure is always closed. And for any x in omega, if we have this true, then because this is continuous over the omega bar, or the closure of omega, so we can easily show that this is less than or equal to L0 or L0 for any x in omega bar. Okay, because of continuity of f. But the issue is with this. Well, when we are in the interior point, at an interior point, we know how to do the gradient because we have this omega, right? It's open, so every point is an interior point. I can draw a ball, and then we can talk about the gradient easily. But if it's on the boundary, it will be an issue, right? We need to specify what the gradient means there. So to avoid this issue, we just say that the gradient is defined, or any derivative is defined in the interior of omega. Or to be more simplified, we just say that omega is open, so every point is interior point. Okay, so that's just make things statement more simple without losing any rigor right here. Okay. Okay, let's say that we have this set M, and then this F is sequentially compact in L1 in C1. Okay, then F is sequentially compact in C1. Okay, since we have the Arzela Ascoli theorem, we just need to show that it is is uniformly bounded and equi-continuous. Well, apparently it is uniformly bounded by this L0, okay, because no matter what x is, the f of x is bounded by that, so it's uniformly bounded. We just need to show that it's equi-continuous as well. Well, this is actually a very useful trick. You look at this one, this property here. When you see that the gradient is bounded by some number, that means this function is Lipschitz continuous with the L1 as a constant, Lipschitz constant. Okay, why is that? Let's see, for any x and x prime, I look at the difference between them by using the mean value theorem. I know that this one is equal to the gradient of f at some point in between them. Usually it means that if I have x here and x prime here, and then you need to make sure that there will be some point over this line. That's why I require this to be convex, because for any 2 points in a convex set, any 2 points, their line segment between them or connecting them is completely inside the set omega. Okay, and I know that every point here will be inside omega, so I know that if I use the mean value theorem, the point here, I can either write as c times x minus x prime, or I know that this c is nothing but some point on this line segment. That means I can write it as x lambda x plus 1 minus lambda x prime. Okay, but the point is that this must be inside omega, so that I can apply this right here. I can know that this one is going to be bounded by L1. So this is going to be less than equal to L1 times x minus x prime. So this shows that the f is Lipschitz continuous with constant L1. Okay, and every one of them has this. So Lipschitz continuity is really, really strong. It's probably the strongest continuity you will ever see. It is stronger than uniformly continuous, and definitely stronger than standard continuity. Okay, but right now everyone is bounded by this, has this L1 as Lipschitz continuity. So they are equally continuous with this. Since for any epsilon, you know that you can choose delta to be just epsilon over L1. Then as long as x and x prime is less than delta, then this is going to be less than equal to L1 times this, and this is less than epsilon over L1, since it's less than delta. It's less than equal to delta, which is equal to epsilon over L1, and this becomes epsilon, right? So that's why this condition here gives us equi-continuity. This first one here gives us uniformly boundedness. That's why by the Arzela-Ascoli theorem, this f is sequentially compact. Okay, now let's look at another example. Let's say I have a metric space X and D. Metric space. Okay, and M is sequentially compact. Okay, so it's a sequentially compact subset of X. Sorry, should be X. Okay, and we also have a function f that has an interesting property. This is mapping from X to M. Takes any points in X and that will be mapped to this subset M. And it also satisfies the property of the distance after the mapping between any 2 points is strictly smaller than the f of x1. It's really less than the distance before the mapping. x1, x2. Okay, so this is slightly different from the contraction principle we had earlier, because here we don't really have some theta which is between 0 and 1. We don't have this right now. Okay, it's just a strictly less than. Okay, this is true for any x1, x2 from x. And now I'm going to show the same thing. Show that the f has a unique fixed point on M. Actually, you can see the in X, it doesn't matter. You can easily show that fixed point must be M, because the f takes everything into M. Okay, so we're going to find f(x) such that f(x) equals to f of x. So this is already in M, so that means x is also in M. Okay, so let's see how to prove this. to show this, we first notice that the f must be continuous, right? That's pretty easy to show because of this property. Because for any epsilon greater than 0, there exists delta. Let's just set it to be epsilon. Then, as long as x1, x2 has a distance less than delta for epsilon here, the distance between the after the mapping is also less than epsilon. So it's very easy to show that this f is continuous. Obviously, f is continuous. Okay, now let's say that, let's define this delta. Now this delta is different from the one I just said. I just call a new notation delta to be the infimum of x and the distance between x and fx. Okay, or x is from the x here. Okay. Let me see this time here. So I know that my fixed point, if it exists, must be in M. So that means if the fixed point, it means that x equals to f of x. That means I'm supposed to get some point x such that the distance between x and f of x is equal to 0. Now let's look at the smallest distance I can ever get over this M, and then take this infimum. Eventually, I want to show that the infimum becomes the minimum. And where we reach the minimum, I want to show that at that point, delta is equal to 0. Okay, and in that case, the x will be my fixed point. Okay, so because I'm taking the infimum, I know that there exists a sequence from M such that the distance between xk and the f of xk, this definitely is bigger than or equal to the infimum value, but it's also smaller than delta plus 1 over k. This is the definition for infimum, right? I can find the fact k, xk such that this holds. Well, because of this, we know that the M is sequentially compact, so that I have a sequence here. It must have a convergent subsequence. So that has a subsequence xkj, and also some x in M, such that this xkj convert to M, x in M. Okay, so I know there exists a subsequence, convergent subsequence. I know that they converge to some point in M. So that means here, this one goes to x. So I should say, I look at the xkj, the f of xkj. I know that is greater than delta, less than delta plus 1 over kj. And I know that this one goes to x, this goes to x. But because f is continuous, so this whole thing goes to f of x. And now the distance is also a continuous function. So if this one goes to x, this one goes to f of x, then this whole thing will go to this. Okay. Okay. But the problem here is that if this convert to this whole thing convert to this, and I know that every one of them is squeezed in between this. So that means as a limit, this must be equal to delta. Okay, so let's say that that this is going to be equal to delta. So this is the limit. But the problem is that right now, if I apply f one more time to each of this, then I will get d of f of x, f of x. I know this is true. Okay, if this is different from that, then I'll have this, and this is strictly than this, and it's strictly than delta, and that is a contradiction to the definition of the delta, because the delta has to be the infimum right here. Okay, and this implies that the x must be equal to f of x, because this distance must be equal to 0. Okay, we said that as long as you have two distinct points, so I should say that this 2 x1 is not equal to x2, then you have that. Okay, so this implies that I found this limit x, and the x is equal to f of x, means that it is a fixed point. And to show that the fixed point is unique, it's pretty easy. Say, suppose I have x and xi prime, they're both fixed point of f, then apparently the distance between x and x prime is equal to the distance between f of x and f of x prime. The reason is they are fixed points. Okay, but if they're different, then they should be less than x and x prime, and that would be a contradiction, because we have something less than itself. So unless the sx is just equal to x prime, then we can avoid the contradiction. Okay, in this case, means that the fixed point is unique.